One more. Then we have the next presenter. We are now changing topics. We are changing from the service-oriented architecture to quality of service, TSN. And I earlier said that we only had very few presentations that actually touched the security topic. We had a lot of presentation requests in that applied for the topic of quality of service, TSN. And even in that topic, we had most of them discussing the shapers. But we're doing this after lunch, as said, and before lunch we have one from this complex of TSN specifications. We have these presentations from Razvan Petre from Spirent, who's going to talk on how to achieve redundant time synchronization using 802.1AS-2020 features. So go ahead.
So we are a bit behind schedule here, so I will start with my presentation. It is great to see us in person. My talk today would be about how to use the AS 2020 features and also like what new developments in IEEE are being created there to support fully redundant GBTP. I will briefly discuss why this is needed, why redundant GBTP is needed, redundant time sync is needed for advanced levels of autonomous driving. Also, why this is important, especially in a zonal EE architecture. And then I will briefly touch the new developments, so like the existing feature in 2020, the missing links there, and what's being done to close those gaps to have fully redundant time sync. So sensor fusion combines data from multiple sensors, so different cameras, different radars, LiDARs or ultrasonics. And of course, each sensor has some strengths and some weaknesses. And by using sensor fusion, we can balance the strengths, we can combine the strengths, and we can paint a more accurate image of the environment around the car. So for the different levels of autonomous driving up to level 4, the driver is always the fallback when automation fails. So like when the car cannot handle a difficult scenario, it can always ask the driver to take control. But for higher levels, so for level 4 and level 5, that will not happen. So for that, the car needs to handle all scenarios. So whenever something goes wrong, the car should be able to come to a safe stop. And in order to do that, high availability and seamless redundancy is really a must there. So not only for time sync, but also for other data traffic. But in today's presentation, I will talk about redundant time synchronization. Some example of sensor fusion in practice. So we have, for example, Tesla Autopilot, that's a level 2. It has some 8 cameras, 1 radar. We know that in some regions, they drop the radar. And then for level 4, we have the Waymo driver, where we see that it uses a lot more sensors. So it has 29 cameras, 6 radars, and 5 lidars. And this is truly autonomous driving only in some specific regions, so like in geo-fenced regions. But nonetheless, we see that really sensor fusion is very important when we want to go to higher levels of autonomous driving. So the current trend, the future network architecture in the car is a zonal architecture where different components, different ECUs are connected together, but are connected based on their physical location. And they are grouped together based on the domains that they are part of, but through virtual wires. And that means for the devices that are part of the same domain, in order for them to work good together, they need to be synchronized. They need to have the same notion of time. So that's why time synchronization is very important. not only in the core network, not only in the Ethernet mesh, but also at the edges. For that purpose, for the purpose of achieving good time synchronization, 802.1AS can be used. So the first version of the standards, the 2011 version, is 1588 profile. It is quite highly used in the automotive networks. And after a long version in a draft, a long time in a draft version, AS 2020 was out last year. It was known as Rev until then. AS 2020 introduces some key features that allows us to achieve redundant time synchronization. So the key features are that it allows multiple time domains. It introduces the common mean link delay service. So that means you don't have to measure the link delay on all those different domains, only on domain 0. And it also allows the definition of multiple sync trees. So we can have redundant sync trees. And of course, introduces also a lot more static configuration that is usually desired in automotive networks. So the grandmaster can be defined. Also, the sync trees can be completely defined, so they don't need to be discovered. And as both 2011 and 2020, so 802.1AS was designed to achieve 1 microsecond precision between the nodes, but in practice, depending on of course, the type of the oscillator, the size of the network, and so on, in practice, the performance is much better. So let's see in practice how this can be done. So like if we have a mesh network, if we have a ring there, how can we achieve redundant time synchronization using the AS2020 features? So we can define, we can have the first GM on end station A, but we can define 2 different sync paths. So the dotted blue line and the dashed blue line. And then we can have also another standby GM. So in case the first GM will experience some problems, the second one could take over. And also for the second GM, we can define, again, 2 different sync paths to have a completely redundant path for the time information. To have such a configuration, we will need 4 time domains. Now let's see how such a configuration will behave when fails occur. So let's see, for example, if we have a link failure. So what will happen if the link between bridge 1 and bridge 2 goes down? So it doesn't need to go down permanently, so it can go down for just a couple of seconds there because of a connector problem or something like that. So in that case, we see that some sync path will disappear, but nonetheless, we see that all the nodes in this configuration, all the nodes will have at least 2 different paths of receiving time information. So both from both GMs, they will receive the time information. Now let's see what happens if the GM falls. So like if the grandmaster, the end station A, experience a problem and it goes down. Again, we see that the devices in the network, again, they have like full redundant, still at least 2 different paths of receiving the time information. And the third case, let's see what happens when both the link between the bridge 1 and bridge 2 fails, and also the GM, so the first GM fails. So in that case, of course, you'll have a bit less sync paths to distribute the time information, but still we see that all the nodes will still receive time information. So in this case, only from 1 path, so no redundant there, no redundancy there, but still every node will be able to receive continuous information about the current time of the system. Those are some of the basic building blocks that are available in AS 2020. So AS 2020 has a detection component, so we can detect when something goes wrong, so like when a GM doesn't like send sync anymore. It has a correction component, it has an action component, but nonetheless, it still lacks some parts. And in order to avoid that anyone will go and implement its own way of dealing with these missing links, IEEE started a project. The project is called ASDM. And in ASDM, the aim is to fill the gaps and to define the right components to deal with the missing parts in AS 2020. And those missing parts are a mechanism to determine when a GPTP domain has insufficient quality or like is not up to the task to provide the good time synchronization information. It will define also a function to use to transform the synchronized time of different domains, of two domains into one single time to use by the application. And it will provide a function to direct the synchronized time from one domain to a different domain. Looking into a bit more details about how this is done in ASDM. So ASDM will introduces two blocks, so the hot standby system and the hot standby instance. The hot standby system is the component that provides a single value of the time to the application. There will be one hot standby system for each time scale, and it can be in one of the four states. So it goes from initialization to redundant, non-redundant, and then holdover. Very important, there is no transition like backwards, so there is non-revertive behavior. That means if the system becomes non-redundant, even if the failure is repaired, so even if we have like a link that goes down and then goes up again, the hot standby system will not go back to redundant state unless intervention from a higher layer entity. So this is done on purpose so that no undetected errors will be not noticed. So like we want to have full control when something goes wrong, and we want to have somebody to really know what went wrong and be sure that the fail is completely removed, and then put the system again in the redundant state. The hot standby instance, there is one hot standby instance for each PTP instance. So we have there for a primary PTP instance and a secondary PTP instance. So there will be two hot standby instances. The hot standby instance monitors the PTP instance to determine if the time has enough quality. The quality is not necessarily defined in ASDM, so it is also left to be defined in different TSM profiles. So like for the automotive TSM profile could define its own thresholds for this quality. And it can be in one of four states: not capable, synced out, or not synced. So you have to take into account that ASDM is still a draft, so it's not a approved standard, so things could change, but this is the current state of the standard. When talking about testing redundant GPTP, of course, for example, we see here we could replace different end station or different ports with test ports, and we can measure different metrics to assess the quality of the time synchronization. So offset from the grandmaster, to see if the path delay calculation is done correctly, to see if the neighbor rate ratio calculation is done correctly. But we can also simulate different failure scenarios. So the failure scenarios that we've seen previously, so the link failure or the GM failure, that could be easily simulated with a test tool. And if you have an incipient implementation of ASDM, you could test how that works when these different failure scenarios happens. Although we probably want to have Ethernet in the whole car, we still today have some parts that are not Ethernet, and especially some parts that are CAN. And how to deal when we want to have all the devices, all the sensor or different devices synchronized. Well, AUTOSAR defines time synchronization over CAN. It is a bit similar with what is defined for Ethernet, but it has some particularities. It doesn't measure any link delay. Well, that's not necessary there. It uses two types of broadcast messages, so a sync and the follow-up message. Because there is no hardware time to support it, it needs interrupts from the CAN driver, so to really say when the message was sent by the CAN driver. It targets the worst case accuracy of 10 microseconds versus 1 microsecond on Ethernet, but in practice it achieves around 7 microseconds of accuracy. Usually that's enough, so that's enough for automotive applications. In the future, we have 10-based UNS, and many exhibitors here have some setups showing the new technology, the new 10-based UNS. It has the potential to replace those CAN parts of the automotive network. Unfortunately, AS GPTP is not defined for 10-based UNS, so for multi-drop buses. And normally, there are some problems that can occur inside such a network. So normally when measuring, for example, the path delay, when a slave will send a path delay request, that normally goes to the master, and then the master will reply with a path delay response, and that will get to the slave. But because 10-based UNS is a shared medium, other nodes in the network will receive the same messages and don't know exactly what to do with those. So, and of course, there are different solutions, and again, similar as with ASDM, because it's not desired that anyone will go and implement its own solution for the problem. It's a new group, a new project was created in IEEE, that is ASDS. The part most likely will be approved on the next IEEE plenary happening next week. And this ASDS will try to solve the challenges of making GPTP working on 10-based UNS links. And with this, we come to the end of my presentation. We saw that sensor fusion is important to build a more accurate model of the environment around the car and to benefit from the strengths of different sensors. We need time synchronization, and we need time synchronization in a redundant way. We have the possibility to use AUTOSAR time sync over CAN until we have Ethernet in all the parts of the automotive network. But of course, in order to have GPTP working on 10-based UNS links, some challenges need to be addressed, and this work is carried out in IEEE under the ASDS project. Thank you.
Okay. Thank you. Thank you very much for your presentation. I have a question to you. What do you think would stop car manufacturers from implementing actually the redundant grandmasters or redundant spanning trees in the cars?
I hope nothing, because I mean, there is a bit of complexity, but not too much in my opinion. And I really hope that there will be no roadblocks for the OEMs to adopt this technology.
Mm-hmm. Okay. There's a question from Max.
Yeah, thanks so much. There's actually 2 million questions whenever I read this, and you can read some of them in my comments to ASDM. But the main question I would have is, so any one node in this network has a good chance of receiving 4 time-based signals, 2 domains from every GM. How does it compare that? What does it do if one of those disagree with each other? And what's actually the entity right now? I don't think we defined an entity that takes these 4 time bases, compares them, and then would have a chance of saying, I do a majority voting. How do I select the signal that I actually use from 4 of them?
So just to make it clear, the use case that was presented here, so with having completely 4 different time domains, that's not necessarily the use case inside SDM. So there we are talking about only 2 domains. So this is an extension of that. The way to deal with like the quality of the time on different domains, again, it's, so as you said, you have some comments there, it's still a working standard, so things are still debated, so it's not a published standard. The idea would be that as long as the primary time source is up and running, you don't necessarily decide what happens. Like, you have a quality metric on that time domain, and as long as that one meets the thresholds, you use that one. When the primary time domain is not good enough according to the defined metrics, then you use the secondary time domain for that hot standby application.
Can I add on a question, Kirsten?
Yes. I have one online question, I think, so far, but
I'll make it brief. Don't you think that most of this was covered in the holdover scenario of the avenue specification when we defined bridges to go into holdover when their GM fails?
Yes and no. Depends. I mean, it gives a lot of flexibility of like using the thresholds defined in different profiles. And also here you have a holdover state. So like when both primary and secondary, so like you don't receive any timing information from either the primary or the secondary source, you can go into holdover time, and then the bridges will continue to send timing information based on their local oscillator. If that's good enough, that will be used. Nonetheless, SDM, so it's just you have the option to use it. So it's up in the end to the OEMs to decide if they want to use it or not. If they can live without it, so that's definitely a choice. It's not necessarily intended purely for automotive. So maybe other industry have tighter requirements of the time synchronization. So there is always a trade-off between complexity and the achieved results, and you need to draw a line there. So it's not like the job of IEEE to say use it or not. You have the choice, so they give you the tools to do something, and then you need to decide if that's the right tool for you or not.
Thank you.
Okay, we have the online question.
Yes, we have an online question from Christoph Golub. How do you create the integrity from the different QM time synchronizations?
Could you repeat, please?
How do you create the integrity from the different QM time synchronizations?
So I guess this is related with what Max asked earlier. As I said, like the current idea in the standard is that as long as the primary time source is right, meets the requirements, that is the one used. So like we don't go to the second one. And then if the second one, if the first one doesn't meet the requirement, then we use the second one. So it's not a combine, it doesn't try to combine them as long as the first one is still good enough. I hope that answered the question.
That's all we had on here.
Okay, then thank you very much once more, Razvan.